All right, so we've seen this correspondence between unit quaternions, modulo sine, and rotations. And that's exactly what we want to exploit now going forward. It's the reason that quaternions are going to be so useful to us. But we haven't talked much about quaternion multiplication yet, besides going over the basic rules. So I want to take a closer look at that. So first of all, I want to go back to the idea of composing rotations. So remember that by Euler's theorem, the composition of two rotations is another rotation, right? Two rotations of the sphere, if we compose them, that's actually just a rotation of the sphere about some new axis. But how do we see this new rotation? And how do we see its axis? What is its axis? If you've tried to prove it or seen a proof or gone through the guided proof in Stilwell, then you might have a picture in your head of what that new axis looks like. But even then, it's not easy to see. It's not immediately obvious, okay, bing, that's the axis that we get. If we multiply by 30 degrees about this axis, by 70 degrees about that axis, our new axis is going to be this. We need to draw a few pictures to kind of find it. So in general, it's fairly hard to see it. But an amazing fact about our bijection is that composition of rotations under this bijection corresponds to multiplication of quaternions. This is why this bijection is so useful. And we can easily compute the product of two quaternions, which will then easily reveal the new axis. Remember, when we look at a quaternion, we can immediately see the axis that it's rotating about. It's just literally given by these three coordinates here, A, B, and C. That is the axis vector. So this gives us a very easy way to find that new axis if we can represent our rotations by unit quaternions. So we've already mentioned which quaternions correspond to 180-degree rotations about the x, y, and z axes. I mentioned it, and maybe you remember that it's I, j, and k, these very simple unit quaternions that are just a single part, just I, just j, or just k. Let's quickly verify that. So let's just take the example of I. Well, what would a 180-degree rotation about the x-axis look like? Well, by our formula, it's cosine of 180 over 2 plus sine of 180 over 2 plus 1 times I plus 0 times j plus 0 times k, because the z-axis is just 1, 0, 0. Okay, can we simplify that at all? Well, cosine of 90 is 0. Sine of 90 is 1. So this is just 0 plus 1 times I, which is just I. So I is really is the rotation by 180 degrees about the axis x. Similarly, j and k give you rotations about the y-axis and the z-axis by a 180-degree angle. Okay, what happens if we perform two successive rotations about the x, y, or z axes? In other words, what if we do I followed by I, or j followed by j, or k followed by k? Well, if we do a 180 about x, we get this. If we do another 180 about x, we get this. So it takes us back to where we started. Does that agree with our formula? In particular, does that agree with I squared equals minus 1? Well, it does, because rotations about R3 correspond to unit quaternions modulo sine. So minus 1 is the same as 1 when it comes to rotations. They both represent the identity rotation. So they both take us back to this identity state, that base orientation. So similarly, it's easy to see that a 180 about j followed by another 180 about j, or a 180 about k followed by another 180 about about the z-axis, they all take you back to the identity. And we can actually see this physically. What about this other relation that involves an I and a j? In particular, it says that I times j is equal to k. Can we see this one physically using Bala? And it's important to remember that we always read from right to left. So when we perform this, we want to perform j first and then I. We want to first perform a 180-degree rotation about the y-axis. Then we want to perform a 180-degree rotation about the x-axis. Is that the same as a 180-degree rotation about the z-axis? Well, yes, if I undo that, I get back to my identity. So that is in fact the same. And I wanted to emphasize this here. In this particular case, it doesn't really matter. If you had read it from left to right, it would have still worked, because with 180-degree rotations, these two actually do kind of commute. But in going forward, we have to be very careful to always read from right to left, because when we look at rotations that are less than 180 degrees, it's going to matter a lot. Things are not going to commute anymore. So it's worth testing the remaining rules just as an exercise. So we just did ij equals k, but just for fun, you can try out jk equals I. That should be, or you can try ki equals j. So I'll leave that as an exercise. So let's try something a little more challenging. So which quaternion corresponds to a 90-degree rotation about the z-axis? So I'm now no longer looking at 180 degrees. I'm now looking at just 90 degrees about the z-axis. Which quaternion gives us that 90-degree rotation? Well, the z-axis is 0, 0, 1. 90 degrees is my angle. So just using the bijection, using the formula, what do I get? Well, cosine of 90 degrees is root 2 over 2. Sine of 90 degrees is also root 2. Sorry, cosine of 90 degrees is not root 2 over 2, but I'm not looking at 90. I'm looking at 90 over 2. I'm looking at 45 degrees. So cosine of 45 degrees is root 2 over 2. Sine of 45 degrees is root 2 over 2. So I get root 2 over 2 plus root 2 over 2 times 0i plus 0j plus 1k, because that was my vector here. So that's just equal to root 2 over 2 plus root 2 over 2 times k. So this is my quaternion that corresponds to 90-degree rotation about the z-axis. Visually, it corresponds to this rotation. Okay, so recall that we can achieve a 90-degree z rotation as a composition of 90 degree rotations about the y, x, and minus y axes. So that was an exercise we did in one of the earlier videos. You saw that by doing a y rotation by 90 degrees, followed by an x rotation by 90 degrees, followed by a y rotation by negative 90 degrees, we achieved a z rotation of 90 degrees. Let's just do it quickly to remember. A 90 degrees x rotation is the first thing we do, followed by, a 90-degree y rotation is the first thing that we do, followed by a 90-degree x rotation, followed by a negative 90-degree y rotation. So we get here. And that, we claimed, is the same as a 90-degree z rotation, and indeed it is the same as a 90-degree z rotation. So again, it's very important to read from right to left. Here it really does make a difference. So it's important we did our y rotation first, then our x rotation, then our minus y rotation. And let's translate the statement into the language of quaternions. So our z rotation was given by this quaternion, and it's easy to generalize that and write each of these rotations in terms of quaternions. My 90-degree y rotation is given by root 2 over 2 plus root 2 over 2j. My 90-degree x rotation is given by root 2 over 2 plus root 2 over 2i. And my negative 90 y rotation is given by root 2 over 2 minus root 2 over 2j. So because you can think of it as a 90-degree rotation in the opposite, with respect to the opposite y-axis. I could have also written this as negative root 2 over 2 plus root 2 over 2j, because remember, we're looking at unit quaternions modulo sine. So if I'd written it that way, I'd be thinking of it as a negative 90 rotation about that same y direction. So either one is perfectly fine. So we get a quaternion formula. We get that this quaternion times this quaternion times this quaternion ought to equal this quaternion if quaternions really do represent these 3D rotations nicely, and if I haven't been deceiving you. So does it actually equal that? So as an exercise, can you verify this? Can you check this yourself using quaternion multiplication? And remember, you can remember all of quaternion multiplication with this really handy mnemonic device. You don't need to keep going to the multiplication table. So can you check this yourself?